Hi, I'm Amanda. I'm a PhD student at Sheffield University, and I will talk about a joint work with Michael Vasmer, Joschka, Roffe, and Earl Campbell about single-shot error correction. So let's start with some motivation. Here we are in the error correcting codes picture, where we protect our fragile quantum information by encoding it in a code space using redundancy. In this setting, we assume that the only information we need in order to detect and therefore to correct errors is the result of the measurement of some commuting operators on the system. And this works as long as this operation can be trusted. So as long as the result of the measurements is faithful. But in reality, this operation is fragile itself. It's a quantum operation and undergoes error as everything else. So what can we do? What can we do if we cannot trust these measurements results? And in the literature, two main strategies are proposed. And the first one is to repeat the measurements over time and keep track of the history in order to correct for errors that occurs at this stage. So for instance, if we think of the 2D surface code, we can keep track of the measurements of the signal measurements over time, and then build a 3D surface code where the third dimension is the time. And this strategy works. However, it is costly both resource-wise and time-wise. So the second strategy is the so-called single-shot strategy. And the upside of this second strategy is that has no additional time cost and is resilient against time-correlated noise. So, as I said, our work focuses on the single-shot strategy. And more precisely, what we have tried to do is to understand what is a sufficient criterion for a code to exhibit single-shot properties. So ours is a work in two parts. And the first part, we propose a theoretical framework that encompasses all the known examples up to date of single-shot codes and gives a minimal criterion for codes to exhibit some single-shot properties. The second part focuses on a well-known class of codes, the 3D homological product codes, of which, for example, the 3D tariq code is part of. And we investigate the performances of these codes under noise, both for the qubits, like on the qubit, and on the measurements, obtaining record results. So here we consider stabilizer codes. If we indicate with Pn the poly group on n qubits, then we can choose a subgroup, the stabilizer group, an abelian subgroup of the poly group. And once we have chosen this group, then all the valid code work are going to be the common +1 eigenstate of this group. Once the group is fixed, it identifies a set of correctable error, E. And once we have fixed the group, we can also fix a generating set. And once the generating set is fixed, we can compress all the information that we need in order to perform correction in what is called the syndrome. So the syndrome is a classical bit string that is built as follow. So we measure each of the stabilizer generators, and if on the system we obtain a +1, that the system is in a +1 eigenstate of that stabilizer, we write a 0 in the IT position of the bit string. And if we find a -1, we write a 1. So once our system undergoes the poly error E, what we actually care about is whether this error operator E either commutes or anti-commute with the generating set of stabilizers. And what we assume in this setting is that this bit string, the syndrome that we indicate with S of E for the poly error E, undergoes some bit flip itself, which is represented by a classical bit string that we write as S of E. So just as a warm-up, we can think about the 2D Ising model. So we can put qubit on faces and stabilizers on edges. So for instance, we can say that for any edge, we're going to define a Z operator that has support on the squares that have that edge. So for instance, for this edge, we have this qubit and this qubit. So stabilizer going to have a Z operator here and here and the identity elsewhere. So this is not a full quantum error correcting codes, but is enough to understand what's going on. So in this picture, if we assume that a qubit undergoes, for instance, a bit flip error, so and we highlight that in gray here, and we measure all the generators of the stabilizer group given by the edges, what we find is that the generators, the syndrome support is highlighted in red, and is actually the border, so the edges of the square itself. And in general, if we consider like more general shape of errors, what we find is that in this model, the syndrome is always represented by the perimeter of the error region. And what I'm saying is that we also assume that this is the correct syndrome. So this is the error and the perimeter is the correct syndrome. So if no error occurs at the measurement step, this is what we see. But some error can occur at this step. So for instance, we are gonna detect some flipped syndromes here and here. And what we read is this. So the only information that we have is the syndrome itself. And something went wrong, and instead of having like nice closed loops, we obtain this. And what we know for the 2D Ising model is that the corrected syndrome, so the syndrome that really correspond to actual errors on the system, are closed loops. So if we see this picture, we are able straight away to say that something went wrong here because this is not a closed loop, and something went wrong here. And what we want to understand is that how can we deal with this problem in general for general codes? So before understanding how to deal to this problem, let's first fix the noise models. So we're going to consider two noise models, the adversarial noise model, where we assume that both the error on the qubit E and the error on the syndrome S of E is always correctable. So for instance, is bounded by half the code distance for the qubit error and another quantity for S of E. And the other model we consider is the stochastic noise model, where errors can have an arbitrary location, but the probability of an error to occur decreases exponentially with its size. So errors are sampled following this probability distribution. And what we have to keep in mind is that in the single shot setting, when we assume that syndrome measurements can go wrong, and we just want to use one round of measurements in order to perform correction, we don't ask to completely wipe out the error of the system after one round of correction. But what we ask is just to keep the error under control over time. So in the adversarial noise model setting, what we want is after one round of correction, even if there is some residual error on the system, is the residual error still correctable? I still wait after the code distance? In the stochastic noise model setting instead, what we ask is, there exist values of P and Q such that the code exhibit a threshold after rounds of single shot error correction. So let's start with our foundational results. In a nutshell, we are now able to introduce what our results are. So that you can bear with me with the rest of the talk. So we have two noise models and error on the syndrome. And what we have found is that we are actually able to assess, we have a property that is sufficient for a code to be single shot in the Versailles setting. If we require something more, we will add another assumption. Then we are also able to say that some family of codes have a threshold for stochastic noise. And last, we prove that the well-known class of codes have the property we introduced that we have called confinement, and therefore are single shot in a sense or another. So confinement is the property that we have identified as foundational to understand single shot error correction. And what is stipulated is that there is a relation, a code as confinement, if there is a relation, if we are able to find a relation between the weight of the syndrome and the weight of the error. So, and this needs to hold only for low weight errors. So for instance, in the 2D Ising model, we have the area perimeter low between the weight of the error and the weight of the syndrome. And so this relation holds for low weight errors. Of course, if we have high weight errors like this one, we cannot say anything about it, but this is not in our interest. More formally, we say that a code as TF confinement is if for any polyerror E of weight at most T, this relation holds. And since when looking at the stochastic noise setting, we're actually interested in family of codes, we also propose a definition of good confinement. And we say that a family of code has good confinement if the bound and the weight of the error that is tolerate grows with the length of the code, and the function f is a polynomial. So the important thing to notice here is that we allow f, the polynomial, to be any polynomial. So it can be a linear function, quadratic function, or cubic function. And this is in contrast with the previous definition of confinement that is proposed by Bombin, for instance, or the definition of robustness for expander codes. And this is because in these two previous works, the only confinement function, the only relation that was allowed in between the weight of the error and the weight of the syndrome is a linear one. So the main tool we make use of in order to prove our results is the shade of decoder. The shade of decoder is a theoretical two-stage decoder, and I will now explain to you how it works. So let's first define what a T-shadow is, and which is the seed of the shade of decoder. So let's take a ball in the error space of radius 5, for instance. So in this ball are all the poly errors of weight at most 5. The T shadow, the 5 shadow of the code, is then the image via the syndrome map of this ball. So since ball with the Hamming weight have a containment property, for instance, for the T shadow of the code, so the same. So the 2 shadow of the code is contained in the 5 shadow of the code, and so on. But now, let's suppose that some error occurs, E, which has syndrome S of E, but some other error occurs while measuring. So instead of having the correct syndrome, sigma of E, we give an input to our decoder, a syndrome that contains some error, S of E. The first step is the syndrome repair step. So we take the input syndrome and we look for the minimum weight bit string that maps our input syndrome in the T shadow of the code. The second step is the qubit decode step that takes the syndrome and finds the minimum weight qubit operators that gives rise to that specific syndrome. Of course, if we apply that recovery operator, we are going to have some residual error on the system. And what we prove is that if the code has confinement then there is a relation in between the weight of the residual error and the weight of the error on the syndrome. And thanks to this relation, we are able to keep the weight of the residual error under control over time. And in fact, to prove that codes with good confinement are single shot for adversarial noise, we can use the shadow decoder exactly as I explained to you now. If we further assume that the confinement function is linear, so as in bombing and expander codes example, then we are able to prove that codes with linear confinement have a sustainable single shot threshold. And we prove that by using a variation of the shade of decoder that is based on a notion of weight that we call closeness that comes from percolation theory. However, I will not deep into the details on how to expand the proof of the shader decoder for the adversarial noise to the one for stochastic noise. And I'm gonna now introduce our third and last theoretical result. So the 3D homological product code is just a recipe to build CSS code starting from 3 parity check matrices of classical codes. And what we do is we use the tensor product to build a chain complex, to build a structure like this one. And what we do is that we find a one-to-one correspondence between basis elements of these spaces and object of the codes. So we're gonna have Z stabilizer, qubits, X stabilizer. And here we can see that I have a top layer, the meta check layer, that is not strictly needed by a CSS code, that is very important because will tells us that there is some redundancy in the X stabilizer measurements of these codes and will allow us to decode these codes in the single shot setting, allowing for errors on the X syndrome. So we prove that 3D homological product codes can be embedded on a cubic lattice. And to see how you can do this, let's draw a transversal edge for any basis element in this space, vertical and horizontal. Then, if we overlap these 3 lattices, we obtain a cubic lattice like this one, where possible there is some missing edge, but it's not as important. In this picture, Z stabilizer are in one-to-one correspondence with vertices, and their support is contained in a 3D cross of qubits that is centered in the vertex. X stabilizer comes in 3 types, and they are in one-to-one correspondence with faces. Their support lies on a 2D cross of edges of qubits that is uniquely identified by the face. What we prove is that provided that the classical parity check matrices have some locality and some locality properties, we are able to prove that this locality property is preserved by this embedding. And then, for instance, we are able to see in this way that the 3D toric code is actually a 3D homological product codes. To see how is possible that these codes have X confinement is easier to think about the dual lattice picture. So here we're gonna put X stabilizer on edges and qubits on faces. And then it's easy to imagine how we can find a relation similar to the one represented in the 2D Ising model, where we found a slightly different relation than the one of the perimeter low, because it's a cubic relation, and we are able to prove that these codes have confinement, where the confinement is a cubic function over 2. And as I said, this we have basically proved that all the 3D homological product codes have cubic confinement, which is great. However, theorem 2 says that to have an analytical proof that family of codes have a single-shot threshold, we need the confinement function to be linear. But in the case of 3D homological product codes, we have found a cubic confinement function. But we do believe, and we have conjectured, that actually these codes have a threshold in the single-shot setting for stochastic noise. And we have found confirmation of our conjecture in our numerical experimentation. So we have assumed that both the qubit and the syndrome, the measurement error, are samples following this probability distribution with the same parameter p. And then we have used a two-stage decoder. A two-stage decoder that is not the shade of decoder, that is a theoretical decoder. So our decoder, as a first step, that is the syndrome repair step and exploring the redundancy in the syndrome. So as I pointed out before, if we build that 4-layer chain complex, 4 layers structure, we have a top layer that we have called of meta check that is not needed. And that gives the redundancy in the syndrome, actually. Then the second step solves the corrected syndrome problem, meaning that takes in input a syndrome and find a minimum weight operator that gives rise to that syndrome. So any decoder can be used for step 1 and step 2, and we have implemented 2 decoders. So we either use minimum weight perfect matching for the first step and belief propagation plus order statistic decoding for the first step, while for the second step, we have always used belief propagation plus OSD. As I said, in the single shot setting, we do not ask a decoder to completely wipe out the error from the system after 1 round of correction. So to assess the performance of our decoder, we use the concept of sustainable threshold. So we define PTN as the threshold of a family of codes given n round of qubit noise and noisy syndrome extraction, followed by a last round of noise-free syndrome extraction and correction. Then the sustainable threshold is given by the limit of this quantity as n, the number of rounds, goes to infinity, increases. So in this table, I have reported the results that are highlighted in yellow of our decoder for the toric code, the 3D toric code. So as you can see, in the case of noise-free syndrome, so if we suppose that measurements are always correct, our result is the best up to date and approaches the theoretical optimum bound given by a mapping to statistical phase transition. In the single shot threshold, we outperformed the SWIP decoder of Vasmer, Brown, and Kubica, and we find the best result up to date with the threshold with minimum weight perfect matching and BP plus OSD at 0.9. We also benchmarked our decoder with the 3D surface code, again using minimum weight perfect matching and BP plus OSD. On the x-axis, you can see the number of rounds using and PTN on the y-axis. So again, we found a threshold at around 2.9. And since actually our decoder is quite flexible, so we don't need, we have also implemented a version with BP plus OSD on the first step. We have benchmarked our decoder using a family of 3D homological product codes built starting from random classical matrices. And this is important because minimum weight perfect matching can be used on surface code, toric code, and topological codes. But BP plus OSD is a more general decoder that can actually be used for any LDPC codes. And again, with this class of codes, we have found a threshold at around 2.7, which is close enough to the result for the surface code and toric code. And this is yet another confirmation of our conjecture that this class of codes do have a threshold. So to sum up, we have proposed a framework to understand single-shot error correction. So we have proved that all codes with confinement, a property that we have defined, are single-shot in the Versalian setting. We have then looked at codes that have linear confinement and proved that they do have a single-shot threshold under stochastic noise. Last, we have found a family of codes that do have cubic confinement, and we have conjectured that actually there is at least an overlap with codes that do have an analytical threshold, and found confirmation of our conjecture with our numerical experiments. That's all by me. Thanks for listening.